Hello and welcome to the 21st lecture. So we've been discussing how derivatives affect the shape of the graph, and now we're going to consider the influence of the second derivative on the graph. Okay, so second derivative affects graph. Okay, and we start with some definitions. We say f is concave up on the interval AB if f lies, I'm not sure that's how you spell lies, I sort of think it isn't. Okay. How is well this spelled? If f lies above its tangent plane, on AB. And we say that f is concave down, so let's underline this, concave up, if f lies under its tangent planes. On interval AB. Concave down on the interval AB. Okay, so as always, the picture is much clearer than the words. So let's create a picture. So, for example, something like this is concave up. So we can let this be A and this be B, because if we draw the tangent lines, let's see what happens. Tangent lines always underneath the graph of the function. The graph is curling away upwards away from its tangent lines. Okay? So from now on, we're abbreviating concave up to just C up. Okay? Or we can have something which is C down. Okay, so this is A, and this is B. Then the graph is underneath its tangent lines. Okay, so here's a question that will be very helpful for you to consider. And the question is the following. If we have a function that is concave up, is it necessarily increasing like this? And if we have a function which is concave down, is it necessarily decreasing like this? So good thing for you to do would be to pause the video, think about this question, draw some pictures, and try and answer. If we have a function which is concave up, it has to be increasing on that interval, and if it's concave down, does it have to be decreasing? So pause the video now, think about that, try and come up with an answer, and then press play when you have. Okay, so the answer is no. We can have things that are concave up and are also decreasing like this. And we can have things, graphs that are concave down, but increasing, like this. So being concave up or concave down has nothing to do with whether or not the function is increasing or decreasing, okay? It's about the way that the function curls away from its tangent line. All right, so here's a metaphor. So imagine that you are flying an old style fighter airplane, let's say a Spitfire, okay? And back in those days, you would fire your guns and it would just be like a machine gun coming out from the front of the airplane. So you could see the path of your bullets, right? So if you're flying your airplane and you're concave up, then what are you doing? You're flying along, and as you fire your bullets, if you fire at this particular moment, the bullet comes shooting out like this, exactly along the tangent line to the path of your airplane. At that instant, you fire it off. So you would see the line of bullets underneath you as you bank your airplane up in a concave up style, right? So you'll be banking up like this, and you'd see all these bullets underneath you, right? Similar to this, suppose you're going down steeply, and then you're pulling up the airplane, you know, then you'll be firing your machine gun, and you see all these bullets again underneath you as you pull up, you know, because you're concave up, you're curling up away from your tangents, you know, whether you're going up, whether your altitude is increasing or your altitude is decreasing. If you are in a concave up part of your flight, then you are curling up away from your tangents. Okay. Conversely, if you're concave down, what are you doing? If you're concave down, then if you fire your machine gun exactly at this moment, the trace of the bullet is going to go like this as you bank more steeply down. So you'll see it above you. You'll see it above you. So you're banking down like this, and as you're going down, you can look up and see the trace of your bullets above you. Right? That's concave down. You're curling down underneath your tangents. Okay. Good. So a good thing to do is to practice feeling what this is like by taking your hand and then moving it along where the flat of your hand indicates the tangent plane. So in this case, it's like this, and it curves up, it curves up, it curves up, it curves up. You know, like this, curves down, less down, less down, less down, flattens out. Like this, goes down, less down, less down, less down, less down. Start again. It goes down, more down, more down, more down, more down. Like this, it is up, less up, less up, less up, less up. Okay. So now our task is to try and find, in terms of the second derivative, a condition that describes these things. So let's do it here. So theorem. If f is c up on the interval b, then f double prime, and now a good idea is to pause the video, and I'm about to write an inequality here, okay? And it's either going to be greater than 0 or less than 0, and the best thing for you to do would be to stop the video, look at these pictures, okay, and then try and determine if it's concave up, if it's going to have a positive sign or a negative sign. And maybe you've seen this before, and you remember the answer, but don't, that's no use. It's no good remembering the answer. I want you to have the reason from these pictures, okay? So pause the video now, try and figure this out, press play when you have an answer from the pictures, okay? So the answer is, the derivative has to be positive on this interval AB, and we're going to see why. So what's happening here? Here we have a relatively small slope. Let's say that's 1/10, it's a positive slope, and then the slope gets steeper and steeper and steeper and steeper, right? So the derivative goes from 1/10 to around here is about 1. Here it looks more like 2, and so on. So the derivative is increasing. Yeah? It goes from slightly positive to more positive to more positive. Here we have initially quite a negative slope, so let's say that's like -8 or something, and then it's less negative, less negative, less negative, less negative. Yeah? In either case, wherever we start from, whatever the initial derivative is, as we go along, the derivative is going to increase. So here it goes from -8, and then it increases, so it's less and less negative, and eventually it's going to be 0 around here. Here it is slightly positive, whatever, 1/10, and then it's more and more positive, increasing, right? So when we have something which concave up, since we are curling away upwards, away from the tangent lines, the derivative is actually increasing, yeah? Because the tangent line remains fixed at whatever our gradient was when we were at that point, right? So in the metaphor of the fighter jet, the fighter aeroplane, as we fire our bullets at some particular moment, say here, then we see the history of what our angle was when we fired them off in the path of the bullets, but we are curving upwards away from that. So whatever angle that is, we are going to have a more positive angle here. And same for here. However negative that angle is, as we do this kind of a path, and we're on top of this path, we are going to have a less negative slope than we had when we fired off our bullets. Yeah. So we see that we have to have the gradient increases over this interval where we are concave up. And if the gradient is increasing, then the second gradient, which is the gradient of the gradient, has to be positive, because we've learned that from the previous class, right? And we just know it, it's just clear. If we have an increasing function, then the gradient is positive, just from the picture. So this stuff here, if we're looking at the gradient itself, we see the gradient has to increase. No? The gradient has to increase, and therefore the second gradient has to be positive. So what we have over there is just clearly true from the picture. And similarly from this thing, if we have something which is concave down, right, and we are curling underneath our tangent lines, right, then whatever our tangent line was, as we go forward, then that thing is less negative than what we are now. So we are getting more negative, yeah? We're getting more negative. We're getting more negative, more negative, more negative, yeah? And here we have something which is positive, but then it's less positive, less positive, less positive, less positive, right? Like this, like this. So if we are concave down, the derivative is decreasing, yeah? And therefore the second derivative has to be negative. So let's write that down. Let's maybe even change colors to emphasize the difference. And if f is c down on b, then f double product x on AB. Cool. So that allows us to identify the intervals where we are concave up and concave down. And if you do this, you cannot get this wrong. You will just see it, right? So get in the habit of doing this. Do not memorize these things. Get in the habit of making your hand do a concave up curl like this. See what's happening to the slopes of the tangent lines, right? They're increasing. Yeah? And then you will conclude that you have to have the second derivative positive, and the same for this. Do a concave down curve like this. You'll see that the slopes are decreasing, the gradient is decreasing, and therefore the second derivative is negative. Yeah? Just follows on the pictures. Yeah? There can be no confusing this if you have a picture. Yeah? Cool. All right. Let's see if we have an exercise to do. Yes, we do. Okay, we'll do this exercise and then I'll give you another definition. So sketch a possible graph that satisfies the following. So we have three pieces of information. The first one is that the limit as x goes to minus infinity, f of x is minus 2, and the limit as x goes to infinity, f of x equals 0. So we have horizontal asymptotes at minus 2 and at 0. Second piece of information is that f prime of x is bigger than 0 on minus infinity 1, and f prime of x is less than 0 on 1 infinity. And the third piece of information, second derivative is positive on minus infinity minus 2 and on 2 to infinity, and the second derivative is negative on minus 2 to 2. Okay, so let's try and make some space for these pictures here. Okay, so we're going to learn more about sketching graphs as we go forward. But here's a general beginning strategy to have in mind. So we're going to classify information as 0th order, 1st order, and 2nd order. 0th order is the crudest level of information, and that's the information that we get without taking the derivative. And I've ordered it so that the 0th order is right at the top, and it's just about the information about the horizontal asymptotes. Okay, we don't need to know the derivative for this, it is just given to us here. So let's start to block in the very rough features that we get from the 0th order information. So the horizontal asymptote as x goes to minus infinity is minus 2. So this is minus 2. So if we kind of make this line here at minus 2, then what happens, we have that out here, it's like minus 2, yeah? And the horizontal asymptote as x goes to infinity is 0, so we're going to have some kind of stuff. We don't yet know if it's which way it's going towards, you know, it could be going up and down, more and more close to 0. So let's just put in information like this. So we have a horizontal asymptote as x goes to infinity at 0. Yeah? Okay, that's the 0th order information. And now we kind of use the 1st order information. 1st order means we take the first derivative and see what we got. So we've got that this thing is called positive derivative from minus infinity to 1, and then negative from 1 to infinity. So let's block that in. So this here is 1. So it is increasing from minus infinity to 1, right? And then it is decreasing from 1 to infinity. So we have to have something like this happening. So I'm just going to sketch it roughly, say something like this, yeah? And then it has to somehow decrease, something like this, yeah? Note that it has to cross the x-axis because after 1 it is decreasing, right? So if we were not crossing the x-axis by 1, then we're decreasing, then we can never have horizontal asymptote 0, yeah? So by 1 we definitely have to be above the x-axis, which we do have. Okay, so this is the first and second order information. Yeah? Now let's put in the third order. And the third order is that it is concave up on minus infinity to minus 2, and then from 2 to infinity, and concave down between 2 and minus 2. So this here is minus 2, and this here is 2. Okay, so it's got to be concave up like this until we reach 2, and then concave down, and then concave up again. And that makes sense to us because we can have something which is concave up, whose gradient is gradually increasing, right? But in order for us to start to bend down and then to get the thing ultimately tending to 0 as x goes to infinity, we're going to have that the gradient stops increasing and starts to decrease. Therefore, we're going to have some interval where it's going to be concave down, yeah? And then we can't have it being concave down indefinitely, because if it's concave down indefinitely, then the gradient never can flatten out again. It can never get to 0. So it's always going to be less than some negative thing. So then it'll just head off down like this, and there's no way we can have a horizontal asymptote at 0. Yeah? So this is actually looking good for us because we can put all these pieces together. So let's, on top of this, create something that is concave up all the way up to 2, and then from 2 to minus 2 make it concave down like this, say, and then from 2 to infinity we're going to make it concave up again. Cool. And this green line I just put in as some kind of blocking rough guide towards the 0th and first order information, but the actual guy I want is this yellow graph here, because that does all the things I want it to do. One of the nicer things about this is that if you get this wrong, then often you can't put the information together. You can't find something that satisfies all of this. So for example, there'd be no way to have something that satisfies I and II, but which is concave up the whole time, because there's no way something which is concave up can ultimately flatten down and have horizontal asymptote 0, as I've already mentioned. So, but we can have something which does this, and that does our job for us. Okay, so if you've never done this before, this might seem like a lot of things, but you just take it step by step, right? So we can certainly do I. It's just something we've done before. Horizontal asymptotes, we know that well. We can do II. We've practiced this already. So intervals of increase and decrease. And now the only additional subtlety is now we're learning about the way things curve up or curve down, and there's either concave up or concave down, right? And this does the job. We can put in the tangent lines just to show you more detail. Like definitely concave up around here, right? Concave up, and here it starts to be concave down, so it's underneath its tangent lines. Yeah. Oops. So this is where it starts to be concave up again, and it's going to be above its tangent lines. Like this. Okay, good. Now, well, not final, but now the definition for this particular section. We're going to have to define something called the point of inflection. So point of inflection is a point on the graph, so it's on the graph, so it has two coordinates, it's x and it's y, and it's the point where we go from being concave up to concave down, or vice versa. So we inflect from one type of curvature to another. Something messy. Definition. A point of inflection is the point where we go from C up to C down, or vice versa. So on this graph, the point of inflection is going to be here, which will be minus 2 f of minus 2. So point of inflection is P of C from now on, and here as well. Because, again, we're going from concave up to concave down at this point, and here from concave down to concave up. Cool. All right. So with this background, we can now talk about another way to determine if a critical number has a local max or local min above it. And that's the so-called second derivative test. So the first derivative test is cool because it's going to tell us emphatically what is happening above a critical number. If we go from positive to negative, we have a local max. If we go from negative to positive, the local min. If we go from positive to positive, nothing. If we go from negative to negative, then we have nothing above it. Nothing in the sense it's not local max or local min. But if there is a disadvantage to this test, is that we have to check out the values both to the left and to the right of the critical number. But I should definitely do that too. With the second derivative, we can, in some sense, get the answer quicker by just looking at the value of the second derivative at C. So this is called the second derivative test. Okay, so if C is a critical number, and f prime or f double prime of C, and then blah, 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 then, so this thing is what you are going to fill out in a second. If this, then f of C is a local max. Okay, so again, here I'm going to put an inequality greater or less than 0. The best thing to do is to figure it out for yourself. Yeah? So pause the video, draw some pictures of the local maxes, look at them, and then say if you believe the second derivative will be positive or negative. Okay? When you have that idea, when you have that answer, press play, and then watch me do it. Okay, so what are we going to do? So we're going to draw a picture of a local max. Let's put it over here. So the local max like this, right? Then what is happening? We are going like this, positive to negative, positive to negative. Yeah? So what's happening to the gradient? It's going from positive to 0 to negative, therefore the gradient is decreasing. Yeah? The gradient is decreasing, and therefore the second gradient has got to be negative. Yeah? So this is local max. Yeah? Cool. You can just see that that little shape I've drawn looks like something that is concave down, right? And conversely, if f double prime of C, then f of C is a local min. And why is that? We just draw the picture, right? If we have a local min like this is C, this here is f of C, then what's happening? We have negative, less negative, less negative, 0, positive, more positive, more positive, right? So the gradient is increasing. Yeah? So the second gradient is positive. Cool. All right. So with this test, we can sometimes figure out much more quickly if we have a local max or a local min, because we don't have to test two values to the left or the right, or just figure out values to the left or the right of C. We can just plug in C into F double prime. And that is cool in a way, but it has a disadvantage in that this assumes that we can actually do this, that we can actually take the second derivative of the function at C. And if you think about that more, that assumes that the first derivative exists near C, right? Not only at C, but also near C in order to take the second derivative. So there are examples of functions where this is of no use, right? And a good thing, again, is to think of one yourself. Maybe pause the video, try and think of an example of a function for which this second derivative test won't help you. Yeah? And here's the answer. So, example, well, here's an answer. There's plenty of examples. If we have f of x is just the absolute value of x, right, then local min at 0, because what's this look like? Looks like this, right? So we go from negative to positive, yeah, which is what we've learned. First derivative. By the first derivative test, we've learned that this has to be a local min, yeah? But there's no way to take the second derivative at 0 because it just doesn't exist. The first derivative doesn't even exist at 0. Yeah? So we can't use this test all the time. This is a more special, we can use this in more special situations. And sometimes we just don't want to use this because sometimes the differentiation is such a pain that we don't want to take a second derivative. We'd rather just work with the first derivative and look at the sign change of the first derivative as we go across a critical number. So this is a tool. It's a good one to have. What is really good is if you are doing some exam and you figure out your answers from the first derivative test and then you check them with the second derivative test if you have time. It's very unlikely you're going to simultaneously make a consistent mistake if you do two different tests and get consistent answers, right? So that's a very good thing to do. Yeah. But this is not overall as general as the first derivative test. First derivative test perhaps should be your go-to. Okay, but it's a good one to have. All right, so with these things, now we're going to consider a specific example, and we're going to try and discuss the concavity intervals of increase and decrease, points of inflection on a specific example after I erase this board. Okay, we're going to consider this example. Discuss y of x is equal to x to the 4 minus 4 x to the 3 with respect to intervals of increase, decrease. Increase, decrease is just going to be I/D from now on. And local maxes and mins. And concavity, which means where is it concave up, concave down, so i.e. where is it C up and C down, and points of inflection. Okay. Solution. All right, so we could start by putting in the 0th order information, just information that we know without taking the derivative. And what do we know? We know that for very large x, this thing is sort of out here, right? Because the x to the 4 dominates everything else. When x equals 0, it is 0 for sure. What else do I know? I know that for very small x, this thing is a lot smaller than this, so it's going to be at least going downwards a little bit, and then ultimately it's going to go up again. And for the same reason, this thing is, at least it's going to be above the x-axis for x, which is close to 0 but less than 0. And it's not really what it looks like, because I also see that the derivative will be 0, but that's not really first order information, so that's forbidden at this point. So let's just say the first order information is just that I know it was like this, and it's 0 at 0. Okay, so start again, that's the 0th order information, so 0th order information. Okay, now the first order info. Which we get from taking the derivative. Let's take the derivative. 4x to the 3 minus 12x squared. Let's factor out a 4x squared. And we're just going to have x minus 3. Okay, so I know that the derivative is 0 at 0. Okay, and I also know it is 0 at 3. Yeah, so I want to find out the intervals of increase and decrease, and therefore what I want to do is to find the intervals where either the derivative is positive or negative. And that's going to happen in between these points where the derivative is 0. So the critical numbers, since this is differentiable, the critical numbers are 0 and 3, right? So this here is, say, 3. And between minus infinity and 0, there are no critical numbers. The derivative is always either positive or negative. So it can't cross from positive to negative anywhere between minus infinity and 0, because if it did, then there'd be another point where the derivative was 0. So that can't happen. So it's either going to be above or below 0. Yeah? And from what we know from the 0th order, we'd expect it to be above, but we will check that in a second. And the same here. It's either going to be above or below 0 for between 0 and 3. Yeah? So it's going to be either increasing or decreasing. Yeah? So it's like this, and then from 3 to infinity, same story. So we're going to do the table as we did in the last lecture. So we're going to put the table like this, and we put our intervals. So the first interval is from minus infinity to 0. The second interval is from 0 to 3. And third interval is from 3 to infinity. And then we'll put the terms of this product. Now, just for completeness, I'm going to put the x squared, but this is really always going to, well, I know it's always going to be positive, so it's really not adding much information, but let's just put it there. And then this is the next term, and then we're going to put the derivative here. So no matter what we have, x squared is always positive, so long as we're non-zero, which we always are, so that's easy. This is how we think about. All right, so we have a number which is negative, we subtract 3, it's still negative, so we put negative. Something less than 3, we subtract 3, negative. Something bigger than 3, and we subtract 3, it's positive. So we have negative, negative, positive. Cool. So we have something which is going to be negative all the way from minus infinity to 0, and then it's still negative all the way from 0 to 3. Yeah? So let's block that in, and that's fitting in with our picture. Like this. Yeah, it's flattening out because derivative is 0, but then it continues to be negative. Gradient is negative, and then it flattens out again like this. Cool. All right, and then it is positive from 3 onwards, which does make sense because we know it's positive up here. All right, so that is 0th and 1st order information. Cool. But now we're going to do the second derivative to find out, well, actually, before we do that, we should discuss local maxes and local maxes and mins. So they're only going to come about the critical numbers. The critical numbers are 0 and 3. At 0 we go from minus to minus, so nothing is happening here, and we see it in the diagram. So there's no either local max or local min here. Here we have negative to positive at 3, so negative to positive, so that's a local min. Yeah. So local min at x equals 3. Note at x equals 3. X equals 3 is not the local min. The local min is the value when we stick in 3 into this. All right, now we can do concavity. And we're going to take the second derivative now. So let's differentiate it from this rather than this, because we don't want to use the product rule if we don't have to. So if we differentiate from here, what do we have? We're going to have 3 4 is 12, x squared minus 24, x, let's factor out a 12x, x minus 2. Yeah, cool. So, what do we know about this thing? Same argument as before. We know that y double prime x equals 0 if x equals 0, x is equal to 2. And therefore, on the interval from minus infinity to 0, the second derivative is either positive or negative, right? Because it can't change sign on that interval. And again, from 0 to 2, the second derivative is either positive or negative. And then from 2 to infinity, second derivative is either positive or negative. So let's do a table. So the first interval is minus infinity to 0. The second interval is 0 to 2. And the third interval is 2 to infinity. And then let's put in the factors, so 12x, and we have x minus 2. And then over here, we're going to put the second derivative. Okay, and let's fill out the box, or fill out the table. So, this is negative, this is positive, this is positive. Negative number minus 2 is still negative. A number less than 2 minus 2 is still negative. A number bigger than 2 minus 2 is positive. So negative, negative, positive, positive, negative, negative, positive, positive, positive. Cool. So we have that it's concave up from minus infinity to 0, concave down from 0 to 2, and then concave up again. And let's see if that fits with our picture. So this is 2. Let's say this is 2 right here. And sure enough, that does make sense, right? We can be concave up from minus infinity to 0. We can have this curving like this, right? So it's, tangents are underneath it, yeah? And then from 0 to 2, the tangents are above it, right? And then from 2 onwards, the tangents are underneath it. And it all fits together, it's all consistent. We can create a function, well, the function, the information we've got all makes a consistent picture, and we believe it. We think we've got it right. Okay, good. So, what have we learned? We've learned that if the derivative is positive, then the function's increasing. If the derivative is negative, then it's decreasing. Yeah? That is the first order information. We've learned about second order information, concave up, concave down. Concave up, we're curling above the tangent lines. Yeah? So therefore, the gradient is increasing. Therefore, the second gradient is positive. Concave down, we're curling underneath the tangent lines. Therefore, the gradient is decreasing. Therefore, the second gradient is negative. Yeah? We've learned that when we have a critical number where we can differentiate the critical number, if the second derivative is positive, it's concave up there, then it's a local min. If the second derivative is negative, it's local max. Cool. Oh, we haven't quite finished. We need to identify the points of inflection. Points of inflection are when we go from concave up to concave down. That's going to happen at 0. So this is a point of inflection right here. 0, 0, P of C. And also happens here at 2. So if we put 2 into this, we're going to have 16. What is 4 times 8? 32. So 16 minus 32. 32. So it should be minus 16 here. All right, so that's it for today. I will see you all either tomorrow or next week.